Test? Yeah.
Okay, good morning, everybody. My name is Martin Sivák, and I work for Red Hat on the oVirt project. I've been on the project for about 3 years now. And today I'll show you what one of our side projects that deals with smart VM scheduling. It's a kind of evolution of what we do when we plan VMs. So let's get started. First, I'll give you an introduction about how we do scheduling now and how most of other projects, including the standard oVirt, does scheduling today. Then I'll show you what were our goals when we were actually thinking about doing this. Some theory, because there is some computer science theory behind it. And then I'll describe the optimization service, and I'll show you some hidden endpoints, which you will understand later. So what is scheduling used for in basically any distributed system or any system? When you have virtual machines and you have physical hosts, you need to select the host that will get the actual virtual machine when you want to start it. You have 50 hosts with different load, different capabilities, and you have a VM that has certain requirements, and you need to figure out where to start the VM. That's the first task. Second task, if you support migrations and you click Migrate VM, you need to be able to tell where the VM should be migrated. It's very close to the first task. And the third task is a bit different, because when you have a host that's suddenly too loaded and it has too many VMs, you need to select first the VM that will be migrated away, and then the destination. So how do we do it today? So today we have basically what many people would call a simplified map and reduce and filter approach. This is basically how it looks like. First, we get the list of all the available hosts in the cluster and the VM we are trying to schedule. Then we remove all the hosts that are missing some capabilities. They don't have enough memory, or some network card is missing, not enough disk space, whatever. And we remove all of those. You can see that here. Where's the, oh, sorry. My laser pointer. This is the process. Basically, we are filtering, and only 2 hosts are remaining. And then suddenly we have 2 hosts with the right set of capabilities, but we need to figure out where the VM will actually go. So we have another step, scoring or weighting, as we call it, where we have multiple functions that compute some kind of score. All those scores are summed up, multiplied by weight. You might be interested more in memory load than in CPU load, so you can assign a higher factor to memory, which means we'll multiply the score of memory. And then we'll sum it up all together, and the best host wins. So this is how it works right now. It works like this in oVirt. It works like this in Nova, in OpenStack. It works like this in Kubernetes. Basically, everybody is doing some kind of version of this. Now, it has some limitations. First, it's one-by-one scheduling, which means you start one VM, it finds a place for it, and then you start another VM, it finds a place for it. Second, you have to track pending stuff, which means you start a VM. It's still not running yet, but your user clicked another Start VM button, and you need to be aware of the fact that the VM is going to be started on some host. It's still not there, so you don't see the memory consumption. You somehow need to track the future allocation. We have the pending counters for that. And yeah, the wait for launch versus starting, that's the actual issue we are solving with those. Now, it's one by one, and the order matters. So here you see 2 different runs with the same set of VMs. It's very simplified, but the same set of VMs. You have the left column and right column. And the only difference is that we are starting VMs A, B, C, and D in the left column, and D, C, B, and A in the right column. you see that the result is completely different. The rule here, it's a very simple rule that says use the host with the lowest load. Just because the order was reversed, the situation looks completely different. And we only have one value. We only use memory here, for example. But oVirt uses about 10 different things 10 different values and capabilities to check whether the VM should be run on some host or not. So you see that this is not really optimal, but the advantage of this is it's very fast. If you have the space to start a VM somewhere, we'll start it in a second or so. Now, what happens when you want to start a VM? And this is the same situation, except there are already some VMs running. In total, there is enough space in the cluster, but we want to start a VM that's very huge, and it doesn't immediately fit any host. For that, we need better load balancing, because the VM can't be placed directly. We first need to create space for it. Unfortunately, the current scheduler only does one by one, as I said before, and it doesn't know how to do that. It can't look one step ahead. We need a better scheduler for that. We also want that to be configurable by the current cluster migration policy, and the service is going to use quite a lot of resources, so we need a separate machine for that. So this is the goal. We need to solve this situation, and I'll show you how we did that. So now, the computer science theory. This whole thing is called machine reassignment problem. Basically, you define the problem by a set of machines and set of processes. Each machine has some resources. Each allocation requires some resources. You have affinity and anti-affinity rules. You might want some VMs to run together on one collocated host, or some VMs do not run together because they are using too many resources. The anti-affinity is actually very important in raising the complexity. It's causing the complexity to ramp really up. And because of all that, it's NP-hard problem. If you have computer science background, you know that that's about as hard as it gets. And it's not really solvable by deterministic algorithms. So brute force is a no-go. If you have more than 2 or 10 VMs, it will just take very, very long time to compute that. It will eat all your resources. But we need reasonable response time. We took a look at a competition where some teams were competing in this exact problem. There's the link to it. In 2012, one of our Red Hat teams from the JBoss project competed there actually with their solution. And their solution uses probabilistic approach. This basically means we are not trying to compute somehow what is the right assignment. We are randomly creating assignments and then computing a score. So we throw a dice and we'll somehow spread the VMs across the host. And then suddenly we see, oh, but here we violated the hard constraint. Here it's not optimal because the memory is just too low now. So we give it some kind of score. And then we throw the dice again. What happens is we get another solution, and we can compare the scores. We keep the best one. Obviously, this is also not very efficient because we can revisit the same solution like we did in the past if we just randomly select solutions. So that's not the way to go, not exactly. So what we have to do, we have to use some heuristics and some limitations to the randomness. There are a couple of algorithms that can help you with that. The simplest one, and the one that mostly everybody from the universities is aware of that, is simulated annealing. Simulated annealing is basically modeled according to how steel was forged. And there is some movement of atoms, but as the temperature goes down, the movement is smaller and smaller. In this case, simulated annealing would select a random solution and then modify an assignment. It would move a VM to a different host, but just a single VM. The rest will stay the same. and then it will move the, it will take the migration, but will replace the VM that's actually moved. Basically, you modify variables randomly, but not everything at once, just one by one. And you are moving across the solution space. And with progressing time, you are limiting the amount of movements, you are limiting the distance, so you are only making smaller steps, and then you reach some suboptimal, usually suboptimal solution. That's cool, but we couldn't use that because of the suboptimal solution. There are local maxima. But what we use is tabu search. Tabu search is very similar to this. It actually also moves in the space of solutions. But if we replace the VM and we see that the score was actually lower than before, we return. And we remember that replacing the VM was not a good way to go for a certain amount of steps, 1,000 or 10,000 or so. And then we try a different direction. We get to some other local maxima, and after 10,000 steps, we try to replace the VM again, because suddenly the timeout for the VM replacement step expired. It's better for us. It had better results, so that's what we are using. But we actually tried simulated annealing too, and it's easier to explain. Then we have genetic algorithms. We are not using those because we are running in a single thread. Genetic algorithms are perfectly fit for multi-threaded and distributed system, but that's not what we have. Although it's a good fit for this problem, since we are not running distributively, we can't use it easily. It wouldn't give us any benefit. So now about the projects that competed in the challenge. The project that implements all these optimizations is called Optaplanner. It's part of the JBoss suite, JBoss Business Rule Management suite. And behind the algorithm, there is a drools system. Drools is a rule matching project. Basically, you write a certain set of rules. You have, when something happens, do this action. And Optaplanner builds the heuristics on top of that. Basically, the do something action part is just increase the score or decrease the score. These are very interesting projects. We are in the virtualization track here, and JBoss and Java are in different part of this building, but I actually think there was a presentation yesterday about drools. So if you have any interest in planning, and not just random planning, but even business process planning, drools is a project to look at. So what we did, we have taken drools and Optaplanner, our preprocessor, and we have written a service. It's constantly running service on some isolated VM or separate host, because it really needs a lot of resources, which has one solver thread per cluster. That's why we don't use genetic algorithms, because we only have one thread. And it's constantly improving the solution. So at the beginning, it scans the cluster. It takes a look at all the VMs, all the hosts, all the resources. And it's constantly computing the best allocation according to your rules. If the solution is not improving, it will pause and wait for updates. Every 30 seconds or so, we scan the cluster again, and we feed the changes to the optimization engine. When it receives the updates, it incorporates them into the current solution, and the solution suddenly is not as optimal as it was because some allocations changed. But it can reuse the old solution, and when it reuses that, it's much faster to converge on a new solution. So we are not computing everything from the scratch again. We feed it into an existing solution, and we just let it to fine tailor the solution to the new one. So that's how we save some CPU cycles. So this is the architecture we have. You can see that this part, basically here, that's the standard oVirt architecture. You have some website management. You have a machine that runs the oVirt engine. That's the brain. That's the part that does the scheduling. That's the part that takes track of all the resources. It can be a VM now, but it's not important for this case. Here you have your set of hosts, and on those you run your VMs. That's a standard setup. And here we added a machine or a VM with the optimizer service. So you see the arrows there. That's the direction of communication. So oVirt internally communicates in between the nodes, the engine, the website. But the optimizer only reads data from the engine. It's not sending anything back. And then it sends data, or actually it's polled by the website UI plugin to show the results to the user. The whole optimizer is running as a REST service. So you only have a couple of get and post endpoints, and you can query for data. And it uses REST API to query data from the engine. So this is the internal architecture. It's a bit more complicated, but what it is this is one solver, one thread. We get all the facts from the engine. Then we preprocess them to some other data, apply the factors to your rules, configuration, and then this is the solution. We have a couple of predefined steps. At the beginning, when you configure the optimizer, you select how many steps into the future you want to take a look. Here I only have 5. And some of them are not valid because the VM is not set or the host is not set. But the steps that are valid, we have 2 here, are here and here. They are returned to the user. The user can actually check whether some solution, even manually crafted one, is valid solution for the current cluster. That's actually pretty good for debugging. It's even important for one of the features I'll be talking about in a second. One thing we have is when you have the engine, when you have the management, you can right-click a VM and select Optimize Start. What it does, it records the VM as this VM should be running, and it can do the multiple step start. So it can first create a space for the VM and then give you the result, give you the set of migrations that will result in that VM being on. That's the goal we had. We weren't able to start the VM because it didn't fit immediately. So how do we get data from the engine? First, we do cluster discovery every couple of minutes. So when you add a new cluster, we'll discover it eventually. We start a new solver thread. Then every 30 seconds, as I said, we do cluster updates where we read the list of all the resources. And we use REST API. For performance reasons, we are using the REST API in bulk, which means we are querying for all the VMs and all the hosts in one go. oVirt engine REST API is not the fastest REST API ever, so we had to optimize that a bit. And there are still some things to do to make it faster. Now, cluster facts. What do we actually do with those? So we get the REST entities from the SDK or the REST API. We convert them to objects that can be inserted into the drools database. KIA, KIE is actually knowledge is everything. That's an abbreviation of the drools people. It's a fact database. You have a huge heap of simple objects, or not that simple, but huge heap of objects. It doesn't have any structure. But what drools can do on top of that is pattern matching. So you can ask for a VM with these 2 fields being set to certain value, or you can ask whether some object with certain properties exists. And it's all done using pattern matching. It's all cached, so it's very, very fast. But it eats memory. That's why Optimizer is heavy on resources. So we have the supervised update cycle. Every time we change something, we have to update the optimization service that's constantly running. So it knows to replace the caches or update the caches. We have 3 different fact sets. First, we have cluster state facts. That's the stuff we collect from the cluster. We have configuration facts. We also collect some of your configuration. If you set your cluster to be equally balanced or power saving, which has different set of rules for how the VMs should be allocated to which host, we collect that too, plus user requests. Currently, that's the start with the VM. Some entities are preprocessed, basically because the REST API entities are pretty deep and pretty complicated, and the caching mechanism in the rules only caches top-level objects or accesses to top-level objects. You can't replace something that's deep in the structure. You have to replace the full object. So we preprocess stuff to VM info, host info, just to make it faster and actually more readable when we access the data from the rule system. Now, the difference currently, and any optimization actually relies on the model to be perfectly matching the world, the domain. Unfortunately, currently it's not the case. We are pretty close, but not as close as we would like to be, because in the engine, that's the internal scheduler, one by one, we have policy units, and those are standard Java classes with algorithms and computations. And we have direct access to the engine database, and we have much more data there. The optimizer is using REST API. It's not getting all the data the engine actually has in the database. We are improving that, but still we are not getting everything. But it's using pattern matching, it's declarative, and it's pretty easy to read, although I'll show you a complicated rule that might not look like that to you. But it's not hard to read. You can use collection sum of values, but you are not doing any algorithmics. You are not writing your for loops and doing some multiplications. It's working a bit differently. So the exact match is not achievable right now, but we are getting closer. So this is how a simple rule looks like. You see, this is even valid when you think about drools in general, but this is a rule for optimizer. We have just two sections, when and then. When each line is one rule, this one is split, but each line is one rule, and all three rules, all three subrules have to be valid for the then section to be executed. So in this case, we are looking for a migration step. That's a common line for every rule we have, basically. And then we are checking for whether there is a VM that's not assigned anywhere. And running VM is one of the objects that represent the fact that the VM should be running. So if we have a VM that's not assigned to any host, and it should be running, that's clearly a violation of a rule. So we decrease the score by 10,000 in this case. That's pretty steep price to pay. But although the VM that's not running is also a pretty steep violation of the rules. So, and this is a complicated rule. You see it got a bit more dense. There is a collection in here, accumulate. It basically computes all the memory consumption of all the VMs from a single host, so we can check that there is enough space for a new VM. This is just as an example. It's actually simplified. It's a bit more complicated now. So this is a complicated rule. So you see, it's still not that hard to read, but it can get a bit more complicated. It's still not Java, though. So now, what we compute, when we have all the information and we ask for the solution, the first attempt was just to compute the ideal solution. I have my VMs, I have my hosts. What's the best layout? Well, we got best layout. You see, this is the rule that says the biggest VM should be on the second host, for example. It's an artificial rule. So the best layout is here. The biggest VM is on the second host. The others were moved to the first host. And that's, from this point of view, it's a perfectly valid solution. Unfortunately, it's not reachable. When you try to migrate the VMs over, you see that at one point during migration, you don't have enough space to actually do it. Well, so we improved that. We replaced the code a bit, and then we started doing the migration steps. So that's much more complicated in terms of algorithmics. It's much more complicated in terms of resource usage, because suddenly you are not computing one final state. You're computing some intermediate states too. But it actually shows you that this solution is not possible. So although the result is desirable, it's not reachable from the system like it is now. It might be in a Docker-based cluster, for example. We don't support it, but if we use something like that for Docker or maybe for OpenStack, they can shut the VM down and then start it again on a different host. For them, that's a viable use case. Unfortunately, oVirt treats VMs as pets, which means we won't kill a VM ever if we can avoid it. So we only rely on live migration, and you see that with migrations, it's not possible to reach the best scenario. It's slower to converge, but hard constraints are checked for every step. Soft constraints are only checked for the result, because we don't care if the score decreases temporarily during the migration procedure. but at the end we'll get better cluster balancing. Now, how we report results? We have REST interface. We have one endpoint per cluster. It's oVirt optimizer /results/cluster. It gives you JSON. I'm not sure how well you can read that because it's pretty small, but basically you get preprocessed settings. You get preprocessed host to VM map. You have preprocessed VM to host map. You have migration steps. You have the current situation. It's all done this way. Some kind of noise and echo probably in the sound, but it's all done so your JavaScript or whoever is processing the result has to do as few computation steps as possible. You can just take this and display it on a website without any complicated processing. And this is how it looks like when we process the JavaScript. The JSON into JavaScript. You get a page with solution status. It tells you that the solution is doable or not doable at all. It shows you the migration steps that are planned for you, and you can either execute them or cancel them. There is no automatics. We only create a hint for the sysadmin currently. We plan on having some automated stuff in the future, but we were afraid that it might start migration storms in production clusters, and we couldn't risk that since it's basically a tech preview. So we only created it as a hint for sysadmin, and there are buttons that will start the migrations, but the sysadmin has to confirm those. So we show the destination, the result situation. That's the bottom here. For each host, we'll show you the VMs that will end up being there with all the buttons to start migrations. We'll show you the VMs that are supposed to be started. We'll show you the migration steps. That's what you'll see. It's all correlated using UID from the engine. As I said, applying the solution is manual at the time, and we are monitoring status. When you start a migration or start a VM, we'll actually show you what's happening. Now, there is a solution freeze button. Solution freeze button is important because when you compute 30 steps, and each VM has 4 gigabytes of RAM, for example, it can take some time to actually migrate the VM. And you want to wait for the VM to be fully migrated before you start another step. Because otherwise you don't have the space you might need for some other step. So since we change the solution every 30 seconds or so, the solution that you had at the beginning might be completely different from what you get from the optimizer at the end of your procedure. But you might have liked the first solution and you just want to go to the end of it. So you can freeze the solution. If you freeze it, we won't update the web page. Obviously, the optimizer is still running, but we won't update the web page, and you can click the buttons. What can happen, though, is that somebody else does some kind of migration too, and your solution is no longer valid, which means, he took the space you prepared for some other VM. So although we've frozen the solution, we are still constantly sending the solution back using one of the endpoints I've talked about before, and we get the score back. We are not running an optimization on your solution or on the existing solution. We are just recomputing the score just to see whether it's still valid or not. And if it's still valid, we don't do nothing. If it's not valid, we'll tell you that, hey, your solution is no longer valid, you might want to refresh the page or unfreeze it. That's one of the things. So even though you freeze the solution, we still constantly talk to the optimizer. Now we have a couple of hidden gems. You can write your own custom DRR rules using the drools language. You just put them into etc over optimizer rules.d. We'll automatically scan them and include them. If you have a typo in there or a syntax error, it will blow up, obviously. It will not start. But if it's correct, it will start, and it will start using your rules. You can use all the pattern matching magic. The standard set of rules is part of the project. It's internal, so you can't replace that, but you can add your own. Like VM for this customer has higher priority, stuff like that. We have also simple scheduling. Basically, at the beginning, I talked about how the scheduling is done in all the projects today, basically all the widespread projects. We have the same thing in the optimizer too. If you want to run optimizer without the optimization engine to save resources, but if you want to use the rules, you can just give it number of steps of 0. It will not start Optimizer, but it will still allow you to post a specially crafted JSON with all the information to an endpoint. And it will give you a list of hosts and their score. And then you can select the best host and use it as destination. It's very cheap in terms of computing power because it's not running the optimization. And if you just want to have the same set of rules for Optimizer and a simple scheduling, that's how you can do it. You can have the same service provide you both, even simple stuff, even the complicated stuff. It's useful for starting a VM. When you have enough space for starting a VM, you might not want to run the full optimization just to get the one step that tells you start it on this host. Because that can take time. The optimizer is a non-deterministic process. And that means that it can take 30 seconds, it can take 2 minutes because it can select bad random solutions. But when you click the button, the user expects when a user clicks the button, he expects the VM to be started pretty fast. And if there is enough space for the VM, there is no reason to use the optimizer for that. So you can use both approaches. You can use the simple start or simple scheduling for starting the VM if there is enough space, and the optimizer part to starting a VM when there is not enough space and for migrations. Then we also have debug endpoints. You have to enable those in the config file because they expose all the information about your cluster. But basically, you can create a dump of the full KAI database. So you get all the stuff in JSON, and then you can submit it back. That wouldn't be too useful, but when you are submitting it back, you can actually modify it. So you can manually do changes to the JSON file to see what will happen, basically to test for responses to some different scenarios you might have in your cluster. So you can use it as a test bed for checking the score when you change VMs or you add a host. We use it for debugging, obviously. When you run the master version, because it's not in the released version yet, but when you run the master version of Optimizer and you find a bug in the scheduling part, I mean, it's not treating my VM like it should be, you can create the dump, send it to us. We can import it to our optimizer without having your cluster. It's not necessary to have your setup then. And we can see the rules and everything that was applied. Now, future plans, tighter integration with the business rule management system. That's the JBoss part, especially with regards to deployment and RPMs. Because currently you have to download a zip file on Fedora, and in oVirt world, we'll do it for you from the RPM package with all the checksumming and everything to make sure it's secure. But if you are using the supported version of Red Hat Enterprise Virtualization, we can't do that. So there you have to download a zip file and execute oVirt Optimizer setup script that will unpack it and prepare everything. Full automation of the optimization, that's what I said. Currently, the sysadmin has to click all the buttons. We can provide automation, but we don't have it yet. We want to be pushing cluster data updates to the optimizer instead of polling the engine. Because currently we are polling every 30 seconds. You can configure the time, but the default is 30 seconds. And that's not efficient. First, we are polling even when nothing changed. Second, we are polling only every 30 seconds. And when a huge change is undergoing in the engine, we should be doing that more often. Support for more policy units. The internal policy, the drools file, is missing some rules we have in the engine. We don't have them in the optimizer yet. It takes some time to write them, test them, and we just don't have that many developers working on that. Too bad. And we want to review OpenStack, Gantt, then Kubernetes, Mesos, all the other projects like that. Because we might be able to work with them and to write their own preprocessors for the optimizer. So they would be able to utilize it as well. So how you can test it yourself? Well, you install oVirt. You have a couple of hosts. You install this repository. It will add all the necessary files to your configuration. Then you just do yum install oVirt engine on one, and yum install oVirt optimizer on the other one, and you will configure it and prepare it. On this page, there is a set of steps you can perform to install it manually. It's the upstream version. You see that the feature is called Optaplanner. It was meant to be Optaplanner integration because Optaplanner is the library behind that, and we didn't have oVirt optimizer name when we started the project. It's kind of hard to change the name of the wiki page, so everybody finds it. So yeah, the other way you can use is I have a GitHub Docker file which you can use to create a Docker image on your own machine. You still need the engine, you still need to have the source of information, but you don't have to install a machine for the optimizer. You can just run Docker image on your system. And I think that's it. I would like to show you a demo, but I don't have a VPN connection, unfortunately. So just one screenshot how it looks like. You already saw this page. But that was it's a sub-page in a frame. It's integrated into the oVirt engine. So this is the engine management part, showing the list of clusters. You select cluster and there is a subtab, optimizer result. And that will switch to this page, and there you see everything. So that's it, thanks. And if you have any questions, I have some nice scarves in here. Define future scars. Sure.
So, it's not very clear from the slides the constraints that you have. So, for example, host memory is one thing. So you should have enough memory in the host to place the guest that you want to place. But are there other constraints such as storage device, for example, has at least given performance?
Okay, so the question is that I talked about having constraints like this host has enough memory, and the question is whether there are constraints like a storage device needs to have enough space or NICs are present, for example. Of course. We have constraints with regards to memory, CPU load, networking devices, pass-through devices. Actually, I don't remember all of them. There is special configuration for display network because we support different virtual networks for transferring the display data if you open your VNC or so, and for the management and for storage. We don't have any rules for storage because in oVirt, storage is managed separately. We have a shared storage, so if you have the VM, you have the storage. We access it over network, so the host doesn't have to have enough storage. But yeah, we have quite a lot of rules. I think the number is about 20 right now. And the optimizer separates some of those into multiple rule sets because we also have minimum guaranteed memory and an actual memory. Minimum guaranteed always has to be there. The actual maximum value is good to have, so that's only soft constraint. If it's not there but the guaranteed is still there, you can start a VM. Yeah, so sure.
Just a question.
Okay.
Is it possible to create additional, let's say, variable where you can track, additional resources, like you specify like a network storage? Is it possible to, for example, create some kind of additional resource, define, and just to track this using some kind
Okay,
of
so the question is whether it's possible to define additional resource to track in the optimization in the oVirt. It's possible in oVirt engine. We have something called external scheduler where you write your own internal policy unit for the oVirt engine. I'm talking about the Java part now in Python. And there you can do whatever you want using REST API. The integration with that is not yet present in the optimizer. That's one of the goals too. We want to scan for units that are provided by the Python part. But the drools language is pure Java. I mean, it's pattern matching, but all the lines are pure Java. So you can call whatever Java function you want. Of course, if you call something that's heavy on resources or slow, you will slow down the whole optimization. So, okay.
Is it possible to use it also for moving VMs from one cluster to another, or maybe implementing some kind of aggressive power management and power saving, for example, during the nightly period for data center?
Well, as I said, it's not, okay, sorry. The question is whether it's possible to use it for an aggressive migration management, like power management during night. As I said, this is just a rule engine. So it will propose steps, but it's not actually executing the migrations.
When it will be ready, it can also be used for that even?
Yes. Obviously, any migration you can execute can be executed. So obviously, yes, you can execute migrations. And by the way, we have power management in oVirt.
And also, the other question is if it was also useful for moving from one cluster to another.
Yeah, okay. So the second question was whether it's useful for moving VMs from one cluster to another one. That's generally not allowed in oVirt world. We only allow it for special purposes like upgrade, when you are upgrading between different versions. But Optimizer is cluster bound, so Optimizer doesn't know about any clusters, other clusters. It only optimizes in terms of single cluster. I'm out of time here, so thanks everybody. And the 3 people that ask questions can come to me and I'll give them a scarf. Thanks.
1, 2, 3.